Hi everyone. Today we're going to be learning about impulse and momentum. So impulse is very closely related to momentum, but they're not quite the same thing. We can use impulse and momentum to measure the change in an object's motion in terms of the forces acting on it. To begin with, we're going to be defining impulse and momentum, which might be useful, given that we need to know the definition of something before we can actually use it properly. Now, let's talk about the inertia of moving objects for a moment. Moving objects will remain moving unless a force acts on them, right? That's Newton's first law of motion. It takes more force to stop a heavy object than it does to stop a light object or a slow-moving object, right? So the bigger an object is and the faster it's moving, the more force we have to exert to stop it in the same amount of time. So we say that moving objects have momentum that reflects this difficulty to stop them. The momentum of the object is given by this equation here, the product of its mass and its velocity. So product means that we multiply those two together. We can see from the arrow here that it's going to be a vector quantity in the same direction as the velocity. P equals mv. We can use this equation to figure out the units of the momentum as well, right? It's going to be the units of mass times the units of velocity. So multiplying a scalar by a vector produces a vector quantity, and so P is going to be measured in kilogram meters per second, and it's going to be in the same direction as the velocity. Kilogram is our units for mass, and meters per second are our units for velocity. Now we can combine our equation for momentum with Newton's second law, that is F equals ma, right? We start off with F equals ma. We substitute A for change in velocity over change in time. That's delta v over delta t. And now we have mv at the top, and that's the same as the change in momentum, right? So force equals the change in momentum over the change in time. So the force acting on a body is proportional to the rate of change of momentum. That's just a way of putting that last equation into words. F, the force acting, equals delta P over delta T. That's the rate of change of momentum. We can also write it like this. The change in momentum is equal to the force acting multiplied by the time over which it's acting. Change in momentum equals force times change in time. So we call this delta P the impulse of the force, and we represent it with the capital letter I. We can see, because of the equation, that we can measure it in Newton seconds, right? Units of force times units of time. If we like, we can also measure it in the same units as momentum. So that's kilogram meters per second. If we draw a force time graph, such as this one here, then the area underneath the graph is going to be given by force, that's the y-axis, times time, that's the x-axis, right? So if it's just a square, that's pretty easy to see, but it turns out that no matter what the graph is shaped like, the area underneath it is always going to be the impulse. So this will be the impulse, the change in momentum of the object. We can measure an object's change in momentum just by measuring the area underneath the force time curve, if we should happen to have one. And once we've figured out the change in momentum, we can figure out the velocity of the object and how it changes, assuming, of course, we have the mass of the object as well. If we know the momentum of an object, then we can't know its velocity unless we also know its mass. Now, the impulse of a very large force acting for a very short amount of time, such as a tennis racket when it hits a tennis ball, can be the same as that of a small force acting for a very, very long time, right? So if a very small force acts over a very long period of time, it can still cause a significant change in velocity. Momentum and impulse are very important in physics, simply because they're so useful in describing the motion of an object. We can use both impulse and momentum to solve many problems involving motion. And indeed, you'll get many problems involving motion in tests and exams in your physics class. One of the useful properties of momentum is that the total momentum of a system doesn't change. We'll be talking more about that a bit later. Even if we ignore that, though, the relationship between impulse and force makes it a very useful tool for figuring out how the motion of an object changes when a force acts on it. Let's go on to some questions to make sure you understand all of that. Question 1. What is the momentum of a 1,000 kilogram car traveling at 10 meters per second? Now, momentum equals mass times velocity, so P equals mv, and substituting the numbers, we have 1,000 kilograms times 10 meters per second gives us 10,000, 10 to the 4, kilogram meters per second, in the same direction as its velocity. Remember that momentum is a vector, so it always has a direction. Part B. What is the momentum of a 70 kilogram man running at 8 meters per second? Once again, we'll be using our equation P equals mv. Substituting these numbers, we have 70 kilograms times 8 meters per second, which gives us 560 kilogram meters per second in the direction of his velocity. Question 2. How fast would a 58-gram tennis ball need to travel to reach the momentum of a 160-gram cricket ball traveling at 30 meters per second? So, what the question asks is how fast we need to go to make this object's momentum equal this second momentum. So we'll need to find out what that second momentum is. For the cricket ball, P equals mv, that's going to be 160 grams, so we need to convert it to kilograms if we're going to end up with a measurement of kilogram meters per second, times its velocity, 30 meters per second. So how fast would we need the tennis ball to go in order to reach 4.8 kilogram meters per second of momentum? Well, rearranging P equals mv, we have v equals p on m, and substituting in the numbers of 4.8 kilogram meters per second, 58 grams, we end up with 82.8 meters per second, which intuitively makes sense. The cricket ball is about 3 times heavier than the tennis ball, and so the final speed is about 3 times faster than the cricket ball. Question 3. A constant braking force of 5,000 newtons is applied to a moving car over 4 seconds. How does its momentum change during these 4 seconds? Can you remember your equation for impulse? Its momentum in the forward direction is going to decrease, right? Because it's going from a large amount of forward momentum to a smaller amount of forward momentum. That means the change in momentum is in the backwards direction. So our change in momentum will be force multiplied by the change in time. That's our equation for impulse. Substituting 5,000 newtons for the force and 4 seconds for the time, we end up with 20,000 newton seconds, or equivalently 20,000 kilogram meters per second. Now if the car's mass is 1.8 tons, that's 1,800 kilograms, how does its speed change? So we can figure out the speed change by looking at the momentum change, right? So momentum change is 20,000 kilogram meters per second. Our mass is 1,800 kilograms. And so using P equals mv, we can figure out how much the speed will change. We make v the subject of the equation, v equals P on m. We substitute momentum and mass, and end up with a speed change of 11.11 meters per second. And of course, it's in the backwards direction. This equates to 40 kilometers per hour. Question 4. What is the average force that acts on a 1,200 kilogram crashing car if its initial speed is 15 meters per second and it stops in 1/10 of a second? So we need to figure out the momentum and then use our equation for impulse to figure out the force. Force is going to be change in momentum over change in time, right? That's going to be the same as m times the change in v, because m won't change. So all we need to do is look at the change in velocity. It's going to be 15 meters per second to 0. Substitute in those numbers. Mass is 1,200. Velocity is, well, change in velocity is 15 meters per second. And the time over which we stop is 1/10 of a second. That gives us an answer of 180,000 newtons. That's a lot of force. Question 5. For how long does a 2 Newton force have to act on an object to produce the same impulse as a 15 Newton force that acts for 6 seconds? So in this case, we have a large force that acts for 6 seconds. That's going to produce a certain impulse. But we can produce the same impulse by using a small force for a longer amount of time, right? The first thing we need to do is figure out what the impulse is that we're trying to reproduce. So impulse is force times change in time. It's going to be 15 newtons times 6 seconds, which gives us 90 Newton seconds. So we want this 2 Newton force to produce a change in momentum of 90 Newton seconds. So how do we figure out how long it acts for? Well, all we need to do is rearrange this equation to make delta t, the time, the subject of the equation. So it's going to be momentum over force, or change in momentum over force rather, which will be 90 Newton seconds over 2 newtons, which gives us 45 seconds. So if the 2 Newton force acts for 45 seconds, it produces the same change in momentum as the 15 Newton force that acts for 6 seconds. Question 6. Is it possible to apply a non-zero impulse to an object so that its final speed is equal to its initial speed? If so, give an example, and if not, explain why not. So let me ask you a similar question. Is it possible to apply a force to an object without changing its speed? Not its velocity, its speed. The answer is yes, it is, as long as it's a centripetal force. If the object is moving around in a circle, then its velocity changes, because of course there's a force acting on it, but its speed does not. We can apply that to this as well. So it is possible for the object's final and initial speeds to be the same, because the impulse may change the direction instead of changing the magnitude of the velocity. For 1 kilogram mass is traveling west at 1 meter per second, and a force applies backwards and produces a change in momentum of 2 meters per second, 2 kilogram meters per second rather, then the final speed will be 1 meter per second. It'll be in the opposite direction, but it will be the same speed. So it is possible to apply an impulse and have the final and initial speeds be of equal magnitude. So that's the end of the questions. In this section we've learned about momentum and impulse, change in momentum, and how both of these relate to force. Namely, the force acting on an object equals the change in momentum over the change in time.